Hi everyone, so in this video I'm going to go over practice quiz 2. This is basically about liquid-liquid extraction in a lot of cases. So what we wanted to look at here is these different questions, and there's a lot of similarities in these questions, so it's important to have the general idea, which you probably already start to have from the separation schemes. So let's take a look here. All right, so it says, part A, fill in the blanks in the figure below with the major organic compounds. Remember to include the state of matter for each compound. So in this case, we have this molecule here, which is a carboxylic acid. Carboxylic acids are organic acids. This one's got a lot of carbons, so it's definitely soluble in ether, and it says both are ether soluble. So carboxylic acids can be removed from the ether layer with bases. In this case, we have an organic base. This is an organic base because it's an amine and because it has this nitrogen. This nitrogen has a lone pair. That lone pair can accept a proton, making this an organic base. Note that if you don't have a carboxylic acid or an amine, then you probably have, or you do have, a neutral molecule. Now it is possible you get some kind of inorganic compound, but the inorganic compounds will not dissolve in ether, such as sand, which was used in the lab. All right, so let's take a look here. The first thing we do is dissolve in ether. These are both soluble in ether. They're large organic molecules. And then we extract with HCl. So HCl in water is an acid in water. Acids react with bases, not acids. So the carboxylic acid is going to stay in the ether layer like this. All right, this is 2-chlorobenzoic acid, and that's going to stay in your ether layer. It says to make sure to include states of matter. It's here, but I'll put it here again just in case. Okay, then the lower aqueous layer. So what happens? HCl is a proton donor. It's an acid. The lone pair on nitrogen is a proton acceptor. So effectively, this grabs this proton. Now you don't need this arrow. I'm just trying to show you what happens. That lone pair grabs that proton. So we get the ring that just goes along for the ride. The N now has two H's instead of one. Okay, and the other ring just goes along for the ride. So the two rings are just the same two phenyl groups, okay, like this. And the N grabs the proton. This makes this plus, and then Cl minus is the counter ion to this. So the Cl is minus because it's HCl. So we get the H here. This makes this plus. Nitrogen, if you recall, wants 5 electrons, has 1, 2, 3, 4. And then the counter ion is the Cl minus. And this one is aqueous. We then add NaOH. NaOH is going to remove this proton because it's OH minus, and you're going to end up with water. So what you're going to end up with is the same amine that you originally started with at the beginning of the reaction. This neutral amine right here is not soluble in water, so it's going to precipitate out of the aqueous solution. Note that we separated it from the ether, so there's no ether for this to dissolve in. This is done in a separatory funnel. So we drain off the aqueous layer, the bottom layer, because the water is more dense. Then we add the base to the aqueous layer, and what we end up with is solid amine. This is how we do the separations. Part B says, before isolating the compound from the upper layer from the ether solvent, a student adds anhydrous sodium sulfate. And then it says, why is anhydrous sodium sulfate used in liquid-liquid extraction procedures? So again, instead of trying to write this, I'm just going to talk about this. The reason you use sodium sulfate is because anytime you add ether and water, you're going to dissolve some water into the ether layer. If you dry it up, you're going to make, some kind of pasty mess. So you got to get rid of that water. To get rid of the water, we add the anhydrous sodium sulfate. Anhydrous sodium sulfate coordinates to up to 10 water molecules, but we don't know how many it'll coordinate to, and it dries the organic layer. So the purpose of adding anhydrous sodium sulfate is to dry the organic layer before we evaporate the ether and isolate the solid product. All right, number 2 says place an X on the line next to each of the following solvents that is miscible with water. So in this case, we have this oxygen, which can hydrogen bond with water. This one's acetone, and it's miscible with water. So small ketones can dissolve in water. Here we only have 3 carbons, so acetone definitely miscible with water. This one's ethyl alcohol, the stuff you would find in vodka or beer. This is definitely miscible with water, right? Vodka is not 2 layers. And again, it can hydrogen bond with water. So basically this is a small alcohol, 5 carbons or less, so it can dissolve in water. If we look at this case and this case, these 2 liquids are immiscible with water. Why? Because they only contain carbon and hydrogen. This is C6H6 benzene, and this is C5H12 pentane. Both of these 2 molecules only contain carbon and hydrogen. They're nonpolar. Nonpolar molecules are immiscible with water. This one's a little bit tricky, okay? This molecule is polar because we have a carbon here, 2 Cl's and 2 H's. However, it's not very polar. And it turns out that dichloromethane is not miscible with water. It is not polar enough to dissolve in water. So basically, a couple things to remember. Miscible means mixes with water. So in liquid-liquid extraction, you need 2 immiscible solvents. You used ether and water. The other thing that we need to remember is like dissolves like. So small molecules which contain oxygens, okay, whether it's a small ketone or a small alcohol, that tend to be miscible with water. Molecules that only contain carbon and hydrogen are definitely immiscible with water, and dichloromethane is also immiscible with water because although it's slightly polar, it's not polar enough to dissolve in water. All right, number 3 says, what is the molar mass of the compound shown below? Circle your answer, and then it gives you the molar masses of carbon, oxygen, nitrogen, and hydrogen. So the first thing we need to remember is that carbon has 4 bonds. So at each of these vertices, we have a carbon atom. Okay, so here and here as well. Carbon also has 4 bonds, and we don't show hydrogens. So this carbon has 1, 2, 3 bonds shown, so it must have 1 bond to hydrogen. This carbon has 1, 2, 3 bonds shown, so it must have 1 bond to hydrogen. And all of these carbons are exactly the same. They have 3 bonds shown, so they must have 1 bond to hydrogen. This carbon has 1, 2, 3, 4 bonds shown, so it doesn't have any hydrogens. And this carbon only has 1 bond shown, so it must have 3 hydrogens. Now we can count up what we have. Let's go carbons first. 1, 2, 3, 4, 5, 6, 7, and I missed 1 here, 8. So this is C8. Okay, H's. 1, 2, 3, 4, 5, plus 3 more is 8. And then finally oxygens, there are 2 O's. So what we want to do is take 8 times 12.01 grams, and then we want to add that to 8 times 1.01 grams, and then add that to 2 times 16.00 grams. So if we look here, these are just the molar masses. Carbon's 12, oxygen 16, and hydrogen is 1.01. So basically we just add these all together, and because it's a molar mass, we should technically have these as grams per mole, and when you do that math, you get 136.16 grams per mole. All right, so we're back to liquid-liquid extraction, which is the topic of the first question and several of the following questions. It's really important to remember carboxylic acids are organic acids, and they can be separated by adding bases. Carboxylic acid looks like this, okay, this group here. Amines, which are N, they could have primary amines like this one, 2 H's, or they could be secondary amines where they have a carbon containing group and 2 carbon containing groups and 1 H. and they could be tertiary amines where they have 3 carbon-containing groups. So these could be either carbon-containing groups or H's. If it was NH3, then it's ammonia. It's not an organic compound. But these are amines. These are your bases. These can be separated from the organic layer by adding acids. And then everything else is just neutral. So if we look here, this looks kind of like a carboxylic acid, but it's not. It doesn't have an H here. It has an ethyl group here. So this one is an ester. So this is just neutral. But it does have an amine. So this is a basic functional group. This molecule doesn't have a carboxylic acid or an amine, so this one's just neutral. Okay, so this is just a neutral molecule. So if we look here, can we add 5% HCl? Well, 5% HCl will protonate this and remove it from the ether layer, and that will basically, oh, I noticed a typo here, that should be ether, I'll change that. So these two molecules are both dissolved in ether. We add 5% HCl, which is 95% water, so aqueous this. We're going to get 2 layers in our separatory funnel. So our separatory funnel, this is not a very good separatory funnel, but it looks something like this. It's going to have 2 layers. The bottom layer is going to be your aqueous layer, and the top layer is going to be your ether layer. In this case, the molecule A is going to be transported into the aqueous layer because of the fact that it will be protonated. Molecule B will remain in the ether layer because it is neutral and therefore will not be protonated. So is HCl a good solution? Yes, because it will separate them. And it says, yes, molecule A will be in the aqueous layer, which is true because molecule A is a base. It also says, yes, molecule B will be in the aqueous layer, but that's not true. Molecule B will be in the top ether layer because it will not react with the 5% HCl. So that was a little bit long-winded, but hopefully it gives you the idea. In the subsequent questions about this, I'm going to go through more quickly what's going to happen because I spent a lot of time on this one explaining kind of the concepts. So in question 4, I spent a good amount of time talking about this. So for the next questions, I'm going to go through them a little bit more quickly. It says the molecules below are dissolved in ether, made the same typo again, and placed in a separatory funnel. Is 5% sodium bicarbonate a good solution to use to separate the 2 molecules? Why or why not? Circle your answer. So again, carboxylic acids are organic acids, and they can be separated using bases. Amines, which this molecule is an amine, are organic bases, and they can be separated by adding acids. Everything else are neutral molecules, and this one doesn't have a carboxylic acid or an amine. So these molecules are just neutral, and they're not going to be separated out by adding either acids or bases. They're going to stay dissolved in the ether and are usually recovered by drying up the ether with some sodium sulfate and then evaporating the ether. So in this case, it's 5% sodium bicarbonate. This is baking soda. Okay, so if you ever did a volcano when you were a kid, this is what you react with vinegar to get the bubbling of the volcano. This is a base. If we want to remove this molecule from the ether layer, we need to add an acid to protonate it to make the salt. The ionic salt will then be soluble in the aqueous layer. In this case, adding sodium bicarbonate is not going to do that because we're not going to make an ionic compound that is soluble in the aqueous layer. So no, both molecules will be in the ether layer because neither one of them will be the salt that is capable of dissolving in the aqueous layer. All right, so 6 says, the compound below is dissolved in ether and extracted with 5% aqueous sodium bicarbonate solution. The ether layer and the aqueous layer were placed in 2 different beakers. How could the molecule be recovered as a solid? All right, so this molecule is going to be dissolved in ether. We're then going to use a separatory funnel, and we're going to have 2 layers. The aqueous layer, which is also having sodium bicarbonate in it, and the ether layer, which is going to just be the ether layer on top because ether is less dense. Now, if we look at this molecule here, if we add sodium bicarbonate to this, all right, NaHCO3, this is a base. So this molecule is dissolved in ether. This base is going to deprotonate this molecule. So what's going to happen is we're actually going to take this proton right here off. So we get C double bond O minus, Na plus. This is now an ionic compound. Ionic compounds are not soluble in ether. This OH just goes along for the ride. This is salicylic acid. So this molecule is no longer soluble in ether. This molecule would be found in the aqueous layer. We would also end up with H2CO3, which is not stable at room temperature, and it breaks up into water, liquid, plus CO2 gas, and this is why venting is very important. So this molecule, this sodium salt of salicylic acid, sodium salicylate if you will, is now in the aqueous layer. Now we drain this into the aqueous layer into a beaker. So we have a beaker containing water, the aqueous layer, and this compound floating around in this water. If we want to get this back, we need to add an acid to the aqueous layer, because if we take this molecule like this, C double bond O minus, Na plus, bond OH, aqueous, and we add HCl, for example, an aqueous acid, what's going to happen? This is going to protonate this spot. And what we end up with is the original carboxylic acid that we started with again. So we get the salicylic acid back. But salicylic acid isn't very soluble in water. So what happens is you had this sodium salt of salicylic acid, which is nice and soluble in water because it's an ionic compound. We now have this organic compound, which is not soluble in water. So this is going to precipitate out as a solid. So if you want to get this back, this salicylic acid back, you need to add an acid to the aqueous layer. That is how you do this. And a base works exactly the opposite. So to draw a base into the aqueous layer, we add an acid, and then to get it to precipitate out, we add a base to deprotonate it, because again, the ionic salt is soluble in water, but the neutral compound is not, so it will precipitate. 7 says, if a sample of benzoic acid, melting point 121 to 122 degrees, was contaminated with a small amount of phenol, melting point 40 to 42 degrees C, the melting point range would be. So, if you have impure products, it tends to lower the melting point and broaden the melting point range. So that's what impurities do, because now you have another compound in there that melts at a lower melting point. So you get a broader range and a lower melting point. So the answer would be lower than 121 to 122 degrees C and a broad melting point range, which is choice letter C. All right, so the last question, we're essentially asked to make a separation scheme given the reagents above. Now, if you've never used these reagents before, then probably you're not going to use them in the separation scheme. So for example, we have not used acetic acid, or we have not used phosphoric acid. So probably we're not going to use those in the separation scheme. So in this case, the first thing you need to identify is what type of molecules that you have. And in several previous questions, I've talked about carboxylic acids or organic acids. They can be removed from the ether layer by adding a base. Amines, which have nitrogens in them, are organic bases, and they can be removed from the ether layer by adding acids. Everything else is neutral. So in this case, we have an acid, indicated by its name, salicylic acid, and a neutral molecule, biphenyl. So the first thing that we want to do with these two molecules is dissolve them in ether. So we want to add ether. Then once they're dissolved in ether, we want to add something to get rid of this. Now in this case, we want to add a base. I would add a weaker base as opposed to a stronger base because of several reasons, one of which it'll be easier to get this compound back because there'll be less stuff to neutralize. So I'm going to go with 5% NaHCO3. Okay, so this molecule will deprotonate this carboxylic acid. So we're going to end up with two layers, the aqueous layer and the ether layer. The aqueous layer is going to contain the sodium salt of salicylic acid. So we get C double bond O minus, Na plus, and this OH just goes along for the ride, all right, as well as the ring just goes along for the ride. This ionic compound is not soluble in water, and importantly, it is not soluble in ether. The byproducts of this reaction are carbon dioxide and water. So your carbon dioxide is actually going to be bubbling out of solution as a gas, and water is implied because this is the aqueous layer. So you could put water here or you not put water here. I think it's kind of personal preference on whether you do that or not. Aqueous layer implies that there's water. So the ether layer is going to contain your neutral molecule, in this case biphenyl, which is just these two rings. Okay, so I'm just illustrating these alternating single and double bonds with a circle. All right, and because we did a liquid-liquid extraction, we added an aqueous solvent. This is 95% water. There's going to be trace water in your ether layer. Now, we have to isolate these compounds as solids. So we're not going to be done with either side here. We're going to have to do more stuff to both sides. I'm going to choose this side first, but it doesn't matter. You could choose this side first. All right, so I'm going to choose it just because left to right, I don't know. So this is basically this. To get this back, okay, we need to reprotonate this thing. And we can reprotonate this thing with 5% HCl. So this is dissolved in water. We drain this out of the separatory funnel. Now it's in its own beaker. And then we add acid. We're going to get a solid, which is going to contain our now reprotonated carboxylic acid. And this is not soluble in water, so it precipitates out as a solid. And then in our aqueous layer, you're going to end up with some NaCl, some HCl will be left over, okay? But I'm going to just go with NaCl because you get the sodium salt going with this chloride, all right? But the main thing to remember is that this one precipitates out because this compound is not very soluble in water. Now we have this compound, this neutral one, dissolved in the ether layer. Remember that when you want to before you want to evaporate the ether, you got to get rid of the water. So we're going to end up adding anhydrous Na2SO4, the drying agent. We're going to end up with a solid, which is Na2SO4, coordinated to some number of water molecules. We don't know the exact stoichiometry. They can hold up to 10, but it probably doesn't, okay, because we're going to add excess of it. And we're going to end up with an ether layer, which is going to contain our neutral molecule, and ether, of course, because it's the ether layer. So you could write ether again or just have the ether here. I think it's probably the same thing. Then we're going to use the solvent evaporator. So we're going to evaporate our ether. And when we evaporate our ether, we get a gas, which will recondense, which is our ether, which will be separated from our neutral molecule, our biphenyl here. So this is how you're going to separate these two molecules in an acid-base extraction. In this case, we only had an acid and a neutral. You know, you could do it differently if you had different types of functional groups. So I appreciate you watching this video. I hope you've found it helpful, and good luck on your quiz.